Hello, 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 hello. Testing, testing, testing. Great, okay, that's working. Um, so I went away, had dinner. Was feeling a bit tired. Um, actually thought, excuse me, I thought to myself maybe we should walk through that maths a bit better. Um, the maths of the AI stuff. So let's do that because I think whenever I explain it, I'm always losing some of the actual detail of this. And although I get the intuition of it, I get the sums of it, I always get them wrong. So let me see if I can figure this out. So what we need to do is probably clear out this page, actually. This is the goals, that's fine. Well, maybe it's worth keeping, I don't know. Nah, probably not. Okay, let's just get rid of it all. Cool. So, starting from scratch, let's think of this properly. Okay, so if I were to have some test data, I've got this T in here, and this test data, now let's stick with what Grant was saying. I'm going to take an image of 3 by 3, and I'm going to imagine that each pixel has a value, and I would say it's probably RGB, but let's say it's a black and white image, and this pixel is going to be from 0 to 1. That makes sense. And each pixel represents an activation or a neuron. And the reason that is so, let's draw our neuron. In fact, I'm going to draw all 9 of them. See if I can make them a little bit smaller. 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the reason this would be the case is because the test data is saying if the real data that you're looking at has a value of 0.5 for neuron 1 or activation 1, and 0.5 for 2, and 1 for 3, and 1.75 for 4, etc., etc., then this is the actual data put into number form. So now we can apply maths to it, right? Now, on the second layer of neurons, so we've got our actual data. Now, Grant says, Grant being 3 Blue 1 Brown, which is a channel on YouTube, and you should definitely check him out. He says that first things first is to select a random weight for each of these. So although we know the test data is this, we need to start to say, or we need to start to summarize what this image should represent in terms of biasing. I think that's right. I know what it is. I think it's that each neuron represents a pixel, and this is representing oh gosh, because I can't, so I'm a little bit confused because I know that there is the actual number. So let's imagine this is a picture of a number 1, for example. We would have a number 1 and a number 2, and all these pictures down to number 9. Let's do that. Maybe a 0 as well, but whatever. You see, these are characters and these are pictures. And this needs to be told that this test data, after going through some kind of operation, is indeed number 1. And I think Grant was saying that if you put weight into this, you could just randomize it. So you just literally do any random number, plop it in. So let's imagine this says it's kind of see, yeah, okay. So this is clearly showing that I need to revisit this. Let's just get a diagram from his channel and see if we can just try to understand it by doing the working out, essentially. Bear with me. Here it is. And then I want to do, what is a neural network? Chapter 1. Yeah, let's go to that. Mute that. And now this is the perfect diagram I wanted. Yes, that is it. Right. So let's take this as a starting place. So his video denotes that let me see if I can get these named right, because as soon as I name them, they're going to start making a lot of sense to me. So these, let's go for a blue. Can I make that thicker? How do I do that? This one? This? Alright, cool, yeah. So this section is called hidden layers. Maybe I can actually spell this right. Okay. And this is the input. And these are all possible values. See what he calls them though. I think they're the see what he calls them. Trying to get the name. I'm sorry, I can't do this on the screen because it's his video. I don't wanna steal everything from it. So these must be the possible outcomes. I can't find a name for it. Possible outcomes. Okay, cool. So if the input is a division of all pixels and they represent those values like they do here, maybe you can't see it, and this hidden layer is operational, like work done on those numbers to get to the output, then so we need to ask ourselves, why is there two layers in this example? And he was saying that the reason there might be two layers is because if you take an image of like number 9, you might want to, I don't know, dissect it up a little bit. You might say that the first layer will look at this, and this, and this as separate parts. They've gone behind it, unfortunately, but they would look at separate parts, and then the next part might, I don't know, if there's like a pixel like this or a line like this and it's got a bit of anti-aliasing around the side, then you might want to, check against these values, and so that would be that next layer, and so on and so forth. And then you finally get your answer. So due to the equations and workload done on these hidden layers, we can find out what the likelihood of that being the value 0 or 1 or 2, as in literally the handwritten numbers. Cool. So we're going to go with that for now. So the equation I think was that these were labeled A, but this also, and then you got this input. So let's call this input. And this is not just a set of numbers, but there's actually a probability that it was that number. So although we know that these are 1 to 5, these numbers are actually, like, I think it's 0.75% chance that it's the number 1, or 0.3% chance that it's the number 2. And so what we can do is we can add a bias. If you do a bias that is a negative value, so let's say b is -1, or maybe more likely that it's definitely not number 2 because we're putting in the number 1. So this will be a negative value because you're trying to tell the computer that it's done a bad job, or at least the set of equations or work done was wrong. So now we have to think about the equation. Well, if our input comes in, so this is our input comes in. I'm so sorry about the coughing. I swallowed beer the wrong way. This is not part of. This is not the important part of the equation. The input is represented by these A's. So we've got the activation. Let's call this layer and layer. And so I've not put L1 or L2 here because there is something fundamental in the back propagation part of the AI. So when he back propagates, i.e. he asks questions back up the stack, he refers to it as L and L minus 1 because this is the last layer. Okay, so let me just double check what I've just said. It's important that I get this right. I'm not really trying to teach you guys anything because you can just go and watch this video, but it's more about me trying to get it right. And then I'll be able to offload all the info with better insight. Try and find those equations. Okay. Yeah. Okay. That does make sense. So actually, at this point, he's put 0, and I'm supposing that would be 1. He doesn't actually note that. No. Okay, yeah. Doesn't. So let's just put that as 0 for now. So this is a layer. Okay. So A comes in, and there is this weighting that happens. So this seems to be called a weighting, but I think what's really happened is the weighting is actually this part. So there is a line that gets drawn here, and this is a weighting. That's because the number 0.5 goes through some equation that then outputs a value. Then this activation outputs another value. But we want to have all of these values because it's the entire picture, or the representation of the picture, should go into that additional weighting here, or activation layer. So you can imagine each one is going to that node there. So then this will be, let's call this 1 through to n. This would be A1 in layer 0, and then it's going to be. So this is the confusion part, because I don't know why it's multiplication. So if I go and take a picture of what he's doing here, let's do that. And I need to understand why it is a multiplication thing. So he is multiplying these numbers by the weighting, and I think the weighting is the result of that equation. So this like next A here. Okay, so let's say that's right, and he, well, maybe I just change the colors a bit here. So this will be A1 of layer 0, and this will be W 0, 0. So, okay, so this 0, 0, I think that represents the relationship between the 0th activation and the 0th activation. The next one is, no, it can't be right. I need to watch it again. That's so annoying. I tell you what, let's see if we can be a bit more formal about this. So, formal equation for back propagation AI. Let's read this. Otherwise, what I'll have to do is I'll have to pause the video again and go to 14.2. I'll watch the video and try and re-summarize it. But anyway, this kind of thing works in my head because I'm seeing the notation of 0, 1. I just can't quite tell. Like I understand the concept. If we were to summarize this whole thing as W, then it would be this A plus this W, and then you minus the or plus the B, which is the bias, and I see how it all works, but I want to see the actual fundamental understanding of it. And I think it should be easy. I'm just being an idiot. Unfortunately, I've pulled that the wrong side, so let's try this again. Okay. Backward propagation of errors is an algorithm for supervised learning of artificial neural networks using gradient descent. Given an artificial neural network and an error function, the method calculates the gradient of the error function with respect to the neural network's weights. It is a generalization of the delta rule for perceptrons to multilayer feed-forward neural networks. The backwards part of the name stems from the fact that calculation of the gradient proceeds backwards through the network, with the gradient of the final layer of weights being calculated first, and the gradient of the first layer of weights being calculated last. The backwards part of the name stems from the fact that calculation of the gradient proceeds backwards through the network, with the gradient of the final layer of weights being calculated first, the gradient of the final layer of weights being calculated first. This makes a lot of sense. And the gradient of the first layer of weights being calculated last. Let me try and visualize that. I think, well, once again I'm going to get rid of this because I just don't feel it's like helping me much. We do that. There's a lot of sound outside. I think maybe Italy or well Italy or England playing, aren't they? So I wonder who's won. I guess it'd be England. Maybe. Football, that is. Okay, cool. So I can't hear cheering, so maybe England did lose. Who knows? Yeah. Okay. So it is generalization of the. Okay. So the backwards part of the name stems from the fact that the calculation of the gradient proceeds backwards through the network. The backwards part of the name stems from the fact that the calculation of the gradient proceeds backwards through the network. So we're going backwards. With the gradient of the final layer of weights being calculated first. So it's this part first, whatever this part is, 1, and the gradient of the first layer of weights being calculated last. So there is some weighting applied to partial computations of the gradient from one layer are reused in the computation of the gradient from the previous layers. This backwards flow of the error information allows for efficient computation of the gradient at each layer versus the naive approach of calculating the gradient of each layer separately. This backwards flow of the error information allows for efficient computation of the gradient at each layer versus the naive approach of calculating the gradient of each layer separately. So this is saying that the output is proportional to everything that came before it, rather than proportional to its own layer and computation. Backpropagation's popularity has experienced blah blah blah. History. Backpropagation was one of the first methods able to demonstrate that artificial neural networks could learn good internal representations, i.e., their hidden layers learned non-trivial features. Experts examining multi-layer feed-forward networks trained using backpropagation actually found that many nodes learned features similar to those designed by human experts and those found by neuroscientists investigating biological neural networks. Yep. So backpropagation is an analogous. Backpropagation is analogous to calculating the delta rule for a multi-layer feed-forward network. The change in rule for a multi-layer feed. Thus, like the delta rule, backpropagation requires three things. 1. A dataset consisting of input-output pairs. So this is good, right? So this is slightly different from how Grant was saying. So I think this was going to help me. So this is a vector of x with the index and y with the index, where x equals the input and y equals the desired output of the network. Okay. Right, okay. So it is a function that takes an input and gets an output. So if I think about this as an actual function in programming, it would be x goes in and it would be something like that, and you'd be returning after x has done lots of stuff, it returns y, because y is equal to all the stuff that happened to x. Something like that. Cool. The set of input-output pairs of size n is denoted x equals, it's like a piecewise notation, I can't remember now. This x of 1, y of 1. Now that is interesting actually, already interesting, and I'll tell you why. X of n, y of n. Okay, this is interesting because the input goes in the output comes out. The input goes in, the output goes out. The input goes in, the output goes out. This is a chain of events. A feed-forward neural network is required, as formally defined in the article concerning feed-forward networks, whose parameters are collectively denoted as theta. In backpropagation, the parameters of primary interest are W with index and I guess layer of k, ij, there's a comma. The weight between node j in layer k and node I in layer lk minus 1 and b k the bias for node I in layer lk. There are no connections between nodes in the same layer, and layers are fully connected. Cool. So that means that if you have these neurons again, this does not happen, only this. Cool. And it says in backpropagation, the parameters of primary interest are W, K, and I, and J. Okay. So in backpropagation, the parameters of primary interest are W, the weight between node J in layer LK. So W is equal to the activation J in the layer K, and node I in layer K minus 1, so that is going back 1 into the layer, the backpropagation. So K minus 1 is the layer, and B for that layer, the bias for node I in layer LK. There are no connections between nodes in the same layer, and layers are fully connected. An error function, E, X, and theta. So theta is the summary of this output, or no, okay, the operation, which defines the error between the desired output of this vector and the calculated output of this vector of the neural network on input xi for a set of input-output pairs. So this is therefore x, and a particular value of the parameters theta. Training a neural network with gradient descent requires the calculation of the gradient of the error function with respect to the weights and biases. Then, according to the learning rate, each iteration of gradient descent updates the weights and biases, collectively denoted that, according to this. So we got all of that junk that happens here is equal to all of that junk of this layer minus how fast you want, how many layers you want to have with the check. Okay, so this is a differentiation. I see. So how many? Okay, I see. So if this is a line like that, that's a terrible line. Let me just try that again. Here we go. This is an axis. We would imagine that this is how many steps we want to take, because it's the learning rate, and this is the change in the error function. So it might be like this E. It should be the change in E. Delta E as delta E of the output of x. It defines the error between the desired output and the calculated. So for a set of input-output pairs, therefore x, and a particular value of the parameters. So of this layer and this with index t. So this is t. So this will be. This is this. Like that. I guess it's alpha, right? Like that. And then that is over theta. So I wonder what that graph looks like. Okay, let's continue. Okay, that's fine. Right. The backpropagation algorithm. Using the terms defined in the section titled Formal Definition and the equations derived in the section titled Deriving the Gradients, the backpropagation algorithm is dependent on the following 5 equations. I tell you what, I am so tired today. What I'm going to do is, this is actually really helpful. I'm going to make a note of it. I'm going to go through it offline and see if I can make more sense of it online the next time. Because it's just not running in my head at the moment. I'm not firing on all cylinders. Maybe tomorrow I might have a look at this. So I really apologise, but thanks for watching if you did. And it's interesting that we need to know. We need to understand this maths. We need to understand why we multiply. We need to understand why we are doing, or how the sensitivity of these things, how the sensitivity impacts the output, because everything is multiplied by each other and divided by each other. So there's some nuance you need to understand. So let's do that next time. I'll put that as a note here. Need to further understand the maths at play here, and we'll put that as the link. Let's go through it, and I'll speak to you later. Thanks, guys.